Professor Pernal got her master's degree in 1998 in chemistry at Technical University of Łódź, Poland. Then in 2002, she got PhD in chemistry at Florida State University, US. And next, since 2005 up to 2007, she went for her postdoctoral work at the Theoretical Chemistry Department at the Vrije University Amsterdam in Netherlands. After that, she got an associate professor position at the Institute of Physics at the Łódź University of Technology, Poland, to become a full professor in 2018. Scientific interests of Professor Pernal are focused on development of electronic structure methods based on electron density and reduced density matrices for molecules, investigation of spin states of strongly correlated molecular systems, molecular interactions out of equilibrium, and electronically excited complexes. Professor Pernal got many awards and fellowships, like Croto Lecture at the Department of Chemistry, Florida State University in 2018, Award of the International Academy of Quantum Molecular Science in 2015, Marie Curie Intra-European Fellowship in 2006, Postdoc Outgoing Fellowship Column from the Foundation for Police Science in 2004. Professor Pernal is a topic editor in the Journal of Physical Chemistry Letters and a member of the editorial boards of Journal of Chemical Theory and Computations, Scientific Reports from Nature Publishing Group, Chemical Physics section, and the International Journal of Quantum Chemistry. Katarzyna, screen is yours.
Okay. Thank you for this nice introduction. And first of all, thank you for the invitation for the seminar. I think it's a great initiative to put together people from slightly different fields, but still overlapping. So as you will see, my talk to great extent overlap with what you have learned already from Jean-Michel talk. So I will introduce, so actually it's divided into two parts. The first part is more pedagogical, and I will introduce you to reduced functions in quantum chemistry. My goal is to show you that we could, in principle, do quantum chemistry without the wave function, using only reduced functions like density matrices or even density, electron density. But then I will point out to some problems with this approach. And in the end, we conclude that, in fact, we really need wave functions. And the best idea, which is now being developed, is to combine a wave function approach with reduced functions approaches. So in the second part, which will be more advanced, I will show one of the strategies that we have undertaken in the recent years, actually to combine DFT with wave function theories using one of the reduced functions. Okay, so let us start with the setting. So as you know, in quantum chemistry and in computational chemistry, or more general in computational physics, many particle physics, our dream is to solve the electronic Schrödinger equation, unless you want to go to time-dependent equation, but typically we stick to a time-independent equation. And we work in Born-Oppenheimer approximation, which means, can you see the pointer? I'm not sure, but I hope you do. Paulina, could you confirm?
Yes,
we can see.
Thank you. Yeah, so in the Born-Oppenheimer approximation, the positions of the nuclei are fixed, and we are only concerned about electrons. So by solving the electronic Schrödinger equation, we obtain wave function and the electronic energy, both of them. Okay, but as you know, the wave function is an extremely complicated object, very difficult to handle in terms of the storage and, first of all, in terms of computing it. So it's a 4 times n variable object. Why 4 times n? Because for n electron systems, we have 3 Cartesian coordinates and 1 spin coordinate. This makes 4 coordinates per electron. So it's 4 times n. It's a lot coordinates. So it's really a very complicated functions. What are the properties of the electron functions? As you know, the function must be anti-symmetrized. This is what Pauli principle tells us. So it must be anti-symmetric with respect to interchange of the position of two electrons. What does the full wave function tell us about? The interpretation is only for the square of the wave function. And as we know also from school or first year of study, the square of the modulus of the wave function tells us about it's a probability density. So it tells us what's the probability of finding one electron at tau 1, the second at tau 2, and so on. So if we integrate this p function, we get 1, because the probability distribution function must be normalized to 1. Okay, so these are the properties, as we all know. When you think of the wave function theories in quantum chemistry, I will mainly refer to quantum chemistry. So what is the goal? The goal is to find, as I said already, solution to the Schrödinger equation, but actually we cannot do it exactly. It's too complicated already for two electrons. So what we do, we find approximations to the Schrödinger equation. And if you find some approximation, you get the approximate wave function. Of course, if you are given a wave function, you can compute the total energy of the total electronic energy. And there's a simple prescription. You just take a Hamiltonian and it's sandwiched between the wave functions, and you integrate this object with respect to all coordinates, all 4 n coordinates. But now the question is, do we really need the full electronic wave function for predictions of the properties of the systems, or for understanding of our systems, or for the reaction? So basically for quantum chemistry. Maybe it's involves too much information. The question is actually positive. Wave function is like too informative, and we don't need that much information. We can get away with much simpler objects. And as you will see, these are the objects that I call reduced functions. So let's see how they enter. As an example, let's consider kinetic energy. Okay, to get the kinetic energy, you just need to know, and we do need, how to construct a kinetic energy operator, and you get the value of the kinetic energy by integrating this product of wave function times kinetic energy operator acting on the wave function with respect to all coordinates. You see, it's a multi-dimensional integral. We know all this. Kinetic operator is the one electron operator, meaning that it's given as a sum of kinetic energy operators depending on R1, R2, and so on up to Rn. So it means actually it can be shown very simply that this integral that you see here can be written using a much simpler object, which I call lowercase gamma. So actually this lowercase gamma is the one electron density matrix. And take a note that Jean-Michel was calling it one electron density matrix upper letter gamma. I'm using a lowercase gamma for one RDM. Okay, so actually we see that we get the same number t, if instead of using full wave function, we just use this two particle, actually it's a one particle, but depending on two variables, R1 and R1 prime function. So this is the first reduced function that we encountered. As I said, it's one electron density matrix. So we already have a first surprise, right? We don't need full wave function to get kinetic energy. We are good with only one electron density matrix. Let's take a look. So we have a reduction, right? We can reduce 4n variable object, which is the wave function, to only 2 variable object, which is one electron density matrix. Okay, so let's consider a second component of the energy, which is electron nuclei interaction energy. And the same thing happens here. It's even much simpler, a little bit simpler. So the electron nuclear interaction energy, given as here in terms of the wave function, can be obtained. We get the same value if we use a simpler function, which is a familiar electron density. So instead of having the full wave function, you just need an integrated product of the wave functions. And actually you see that we integrate with respect to all but one variable. So we integrate with respect to tau 2, tau 3 up to tau n. and we leave unintegrated R, the first variable of the wave function. That's the density. And it's good enough, right? We don't need anything more than the density to find a value of the electron nuclei energy. And let's move on to the third component of the electronic energy, which is the electron, sorry, I'm going in the wrong direction, which is the electron-electron interaction energy. Okay, so to get the electron repulsion or electron-electron interaction energy, again, what do you need? According to a definition, right, to quantum mechanics, you need the wave function and the operator, electron-electron interaction operator, which is actually a multiplicative two-electron operator. A two-electron operator is an operator which is given as, for example, follows, as a sum of two particle operators. In this case, it's a Coulomb interaction of electrons at positions R1 and R2. So you can easily rewrite this function, this multi-determinantal integrand in terms of a much simpler, only two-dimensional integration, and the function which I call ρ2. So ρ2 is another, the third reduced function. It's an electron per density. It depends on positions of two electrons, which one is at R1, the other at R2. So here we have a reduction from 4n, right? The total wave function depends on 4n variables to only two variables. And this function ρ2 is sufficient to compute electron-electron interaction. Great, so as you see, we can get all terms in electron energy just using only two reduced functions, one electron reduced density matrix and a electron per density function. So to recap this part, we could conclude that in fact we don't really need a full and complicated multi-dimensional wave function. We can get away with just two objects, one density matrix and electron per density, to compute or to find the total electron energy. Great, so it seems like we could really get rid of the wave function in the quantum chemistry completely and be happy with those reduced objects. And in principle, the answer is positive. Yes, in fact, we could do it, and there are computational approaches which are wave function free. I will not talk much about all of them. I will concentrate on the DFT. But there are methods which use only two electron reduced density matrix, and you get the energy by minimizing the energy functional with respect to two particle density matrix. Actually, you can get even to the lower level and use only one electron density matrix. And there's a theory, which is reduced density matrix functional theory, which tells you that it's enough to have one electron reduced density matrix. You just need to find a functional of it, minimize this functional, and you get an exact, in principle, energy. These methods are, okay, they have valid theoretical foundations, so we know that they are in principle exact, but they have the problems like RDMFT requires construction of the functional, which is unknown, and we have to construct approximations. So this situation is a bit similar to DFT. And this method is not as developed as the method or the theory that you are all familiar with, density functional theory. So the most developed and successful wave function free theory, which is based on the reduced function, is the DFT. In DFT, the reduced function is, of course, electron density, right? So there is this magic Hohenberg-Kohn theorem. So this will be a slide devoted to a DFT. It's a DFT in a nutshell. I will explain everything on this slide. So the Hohenberg-Kohn theorem tells us, in simple words, electron density knows all about the system. So it tells us you don't need a wave function. You don't even need a per electron per density. You just need a density, electron density, which depends only on R, X, Y, Z. And then you can find all information about your system, no matter how complicated it is. So it sounds like a miracle, but actually, if we recall the properties of density, of electron density, maybe then it makes more sense to understand, or it will give us some understanding of the Hohenberg-Kohn. So we know that if density is integrated, right, then you get the number of electrons n, and this number of electrons. So density definitely know how many electrons you have in your molecule or in your system. The other thing that the density knows is positions of the nuclei, because if you plot or visualize somehow density in space, then you will see places where density has a maxima, and these are nuclear cusp locations. So we also know, our density knows, you can get the position of the nuclei in your molecule from density itself. Good. So if you know the number of electrons, you know how many electrons you have, you know where the nuclei are positioned, you can construct a Hamiltonian, right? So based on the density, you can construct the Hamiltonian. If you have a Hamiltonian, then you could in principle solve a Schrödinger equation, and then you find the wave function and the energy. Okay, so indirectly, you can get full knowledge of your system just from the density by constructing the Hamiltonian and so on. Okay, so where's the magic? It all sounds reasonable, right? But still, where's the magic of DFT? Actually, the magic is here, and this is, we are back to Hohenberg-Kohn theorem, because the Hohenberg-Kohn theorem tells us that energy is a function of density. So it tells us there is a way to get the total energy only from the density directly. Okay, it says a functional exists, only we have to be smart enough to find this functional. And we all know it cannot be found. I mean, we have plenty of approximations, but we don't know, and probably will never learn about the form, a closed form or explicit form of the density functional. So energy is a function of the density, and to get the energy, once you have a functional, you just need to minimize this functional with respect to the density. That's the prescription that Hohenberg-Kohn theorem tells us. So Hohenberg-Kohn theorem reassures us that what we do makes sense because DFT has a valid mathematical foundation, but it gives us no clue, as we know, how to construct a functional. So the world that we are living in uses approximate density functionals. And as I said, there's a problem with constructing exact explicit functional. It's not known. So actually, if you write the energy in terms of kinetic, electron energy, electron-electron interaction energy, and electron-nuclear interaction energy, only the last piece is known in terms of a density, right? So we only know how to write explicitly this energy in terms of a density. This is quite simple, you see it here. But we have no idea how to write an exact function of the kinetic energy and electron-electron interaction. There has been a trick introduced by Kohn and Sham, that was in 1965, which helped a lot to develop DFT and to turn it into a practical method after the next 20 years, actually. And the trick was to repartition this the energy and to write it in a bit different way. Still, you get the exact, in principle, exact energy, but you write the energy as the kinetic energy of the non-interacting system, this reference system, which is described with a single determinant, exchange correlation functional, and the energy nuclear functional. So the gain or the advantage of this formula comparing to this one is that we know Ts of rho and the last term, and we only don't know the middle term, the exchange correlation functional. We don't know the exact form, so we have to find approximation. So everything that if you ever use DFT, of course, the first thing that you have to decide on is what to choose an approximation for this term, for exchange correlation part. So as you know, nowadays there are plenty, more than 100 exchange correlation functionals, and the whole art is to know which one works for your problem. I'm exaggerating a bit because there is some common knowledge of which functionals are good for which systems. And there is thousands or more than hundreds of thousands papers published every year. So definitely DFT is nowadays a workhorse of quantum chemistry. Most of the applications in computational chemistry use DFT methods or DFT approximations. And it is on the margin, it's interesting to notice that the outburst of papers on DFT, meaning the outburst of usage of DFT, was not after Hohenberg and Kohn theorem was published, which was in 1964, somewhere here. No, actually, it didn't change anything. DFT was still on the margin of quantum chemistry methods. Only after Becke published his functional in 1998, B88 exchange functional, there was an increase in the number of papers, meaning people started using DFT in the 90s, right? So it's not the theorem and the theoretical foundation of DFT which ignited the usage of this method, but appearance of actual density functional approximations in the 90s. Okay, so now we are in the recent 10 years, we were trying to construct universally applicable functionals. So there's this pursuit of universality in functional development. And there are, as I said, plenty of functionals, more accurate than 20 years ago. That's true. But there are still some problems which are not solved in DFT. And we already understand that at least there's one class of problems which will never find satisfactory solutions in DFT. So it means that density is not enough with our approximations to solve problems which are related to so-called strong correlation. By definition, strong correlation of electrons requires having more than a single determinant. In DFT, in Kohn-Sham DFT, we only have one determinant for the wave function, this Kohn-Sham determinant. And we now understand that it's not enough to treat correctly, to run accurate calculations on systems where electrons are strongly correlated. Okay, so we are back to the problem, if we can really, or to the question, can we really get rid of wave function completely and use reduced quantities? So up to now, what we see is that theoretically, yes, we could only construct everything with some reduced functions, but in practice, having approximate functionals in DFT or density matrix functional theories, we see that this is a very difficult problem, maybe not solvable with sufficient accuracy. So recently, it has been like we came to understanding that the best strategy could be to combine wave function theory with reduced functions, for example, with DFT, and to take best from both theories. So in the second part of this presentation, I will show you one strategy that we have undertaken to combine wave function with DFT. But first, let's list a few advantages of the main advantages of both strategies and what we can gain if you do this marriage of DFT and wave functions. So from the point of view of DFT, right, the advantage of adding some wave function information would be that we could get a better accuracy for multi-reference effects for the strong correlation that I have already mentioned, because wave functions are more efficient. It's easier for the wave function to describe the strong correlation phenomena than for DFT functionals. The second thing that is basically DFT is a ground state theory. So when you go to electronically excited states, DFT has problems, which are less for wave function theory. And there are problems with spin states. Again, spin states are much easier with wave function. From the wave function point of view, why would you try to incorporate a bit of DFT into the wave function? So dynamic correlation is very efficiently treated with existing density functionals. So it would make sense to combine at least correlation functional with wave function. And there's a big problem if you have ever run a wave function calculation, like couple cluster or CAS or multi-configurational SCF or something else. you will always notice there is a problem with basis sets, right? So to get good accuracy, we have to use large basis sets, and large basis sets means high computational cost. So in short, wave function calculations are expensive, and we cannot get to hundreds of electrons. It's impossible. And one of the reasons is basis set size, which is large for wave function. In DFT, you can get away with much smaller basis sets. Okay, so combining DFT with wave function would benefit both of the theories, and it would allow to avoid problems of both. Okay, so when you think of how could we combine these two theories, wave functions and density functionals, as I said, wave function theories are not as efficient in treating dynamic correlation as DFT. Dynamic correlation is a short-range correlation. So when two electrons are close together in space, they are correlated, the motion is correlated, and we call it a dynamic correlation. In density functional correlation, correlation density functionals are very efficient and accurate. So the first idea you would have is let's just add a correlation functional to the wave function energy, hoping that we can efficiently account for this dynamic correlation, which is missing in the density functional theory. Actually, this idea is the worst you could have, although it's a very naive and simple, but it wouldn't lead to accurate predictions for your systems. And why is that? Because you would encounter the correlation double counting error, or the correlation double counting problem. By just directly adding correlation functional to the wave function energy, you would count some correlation energy effects twice. So you want to be smarter and actually add something which you derive from DFT to the wave function, but it cannot be simply a correlation functional. It should be a correlation functional, but equipped with a function. This is this question mark. This question mark is a reduced function which knows where you should add more and where you should add less correlation in space. So it should be a local function to keep computation of this part at low cost. And this function, as I said, should be sensible to the correlation which is already included in the wave function part, right? Because, as I said, the goal is to avoid double correlation. If wave function already takes care of the electron correlation, it should be removed from the density functional part. Okay, so this question mark, this unknown function should measure how much correlation a density functional should add. Okay, so let's look for some candidates for this question mark function, which would measure the correlation which is already included by the wave function. So let's consider something which is a function which is called a conditional per density. So what is a conditional per density? It's a per density, and let me remind you that per density tells us about the probability of finding one electron at the position R2 and the other at the position R1 simultaneously. If you divide this per density by electron density, you get conditional per density. And so conditional per density is interpreted as a probability of finding an electron at R2 on condition that the other electron is fixed at position R1. Okay, so far so good. What do you get if you set R1 equals to R2? This is a so-called on-top per density or on-top conditional per density. So this is a bit different. It's a special case of this function. So it's a special position where you compute this function. Namely, this is a probability of finding both electrons at the same point in space at R. Of course, if both two electrons have same spin by Pauli principle, this probability is 0. But if the spins are opposite, the value of the function is not 0, and the value is related to the degree of correlation. If they are less or more correlated, then this value is different. So actually, if electrons are not correlated at all, right? If they don't see each other, they don't care about their existence. In other words, if the wave function is given by a Slater determinant, single determinant, then the conditional probability is simply 1/2 of the density, which makes sense because 1/2 of the density is given to one electron, the other half to another electron. But actually, this gives us the idea of constructing this sensor of electron correlation, which is based on two-particle function on per density. Because if you consider, let's consider a ratio of the conditional per density on top conditional per density divided by this uncorrelated conditional density. So what are the possible values of this ratio? Okay, there are three possible values. The first is 1. If the value is 1, it means that the wave function is not correlated or the electrons are not correlated. Okay, if the value is smaller than 1, it means that electrons avoid each other. So they don't want to be correlated. And already the wave function takes care of the static correlation. And there's not so much dynamic correlation that should be added to the wave function. And another possibility is that the ratio is greater than 1. It means that electrons like to be in their neighborhood. And it means also that they will be very much dynamically correlated. And it's a signal for the density function that it should do hard work and it should provide a large value, which will be added to the wave function energy. Okay, so this ratio actually is what we need. It indicates locally a necessity to include less when x is smaller than 1 or more of the dynamic correlation from the density functional, from the correlation density functional. Actually, this ratio it's interesting by itself in the sense that it gives us some information about some insight into the correlation, nature of the correlation, and nature of the electron state. So let's consider hydrogen molecule in the ground state at equilibrium bond distance. And if we plot this ratio, x, right, as a function of the position between one and the other nuclei, we see that it's smaller than 1, okay? If we stretch the bond, so it's the same plot, but for the hydrogen bond, hydrogen molecule with stretched bond, you see that the value of the ratio drops almost to 0 in the neighborhood of both nucleus. And this makes perfect sense because it tells us that the electrons, that there is only one electron at close to one nuclei and another to another nucleus. So there's no dynamic correlation in the system. Okay. So this would be the information that the amount of correlation energy from DFT should be 0 because all correlation is of the static character and it's already taken care of by the wave function. If we consider another example, boron hydride molecule, the same picture is visible. This is the plot of the X ratio, the red curve, for the molecule at equilibrium geometry. And this is for stretched bond geometry. And you see the X ratio drops to almost 0 in the vicinity of the hydrogen molecule. And it means that electrons close to this hydrogen nucleus are not correlated. So for the DFT functional, it will be a signal that the value of the correlation energy, dynamic correlation energy, should be small. Okay, actually, it can be explained by considering, maybe I skip the slide, it's more technical and we don't need it at this moment. So it may be explained why the value of x is smaller than 1. It can be understood by considering a covalent state wave function. So by just taking a combination of two electron configurations, then analytically it can be shown that the ratio is smaller than 1. So on the other, if we just revert this, it means that the magnitude of x, if it's smaller than 1, it tells us that the character of the quantum state is covalent, or the character of the state of your molecule is covalent. And this is, that's the same slide. We have, to our surprise, actually, we kind of discovered that the value of x is really greater than 1. So it's not only theoretically possible, but it really happens when the molecule is in a specific excited state. And I'm saying specific because not all excited state shows this feature. So here we see the excited state of the hydrogen molecule, it's sigma u. And what actually we see is the plot of this ratio, this localizer of the correlation for sigma u state, plotted as a function of bond of the position along the bond axis. And you see it's great, the value of x is greater than 1 in the vicinity of the nuclei, both of them. So what do we conclude? I told you a few slides ago that this observation, if x is greater than 1, it tells us that electrons are close to each other most of the time. So the dynamic correlation is large. And actually, that's how we interpret it. But it's more than that, because for us, it also means that the amount of dynamic correlation energy from DFT that will be added to the wave function, part of the energy should be increased, because we want to account for this increased dynamic correlation, which we call enhancements of dynamic correlation. And it's not a peculiarity of the hydrogen bond. We have found that this behavior of this phenomena for other molecules in specific excited states. This, as you will see on the next slide, will be ionic excited states. So this is another example of ethylene molecule, B1U excited state of this molecule. And again, we see that in some regions of space, the ratio, this X ratio, is greater than 1. This is the red area. So it's more general than what we see. And actually, we have pointed to, linked this behavior of X greater than 1 to the ionic character of the state. It can be shown again analytically on the simple model that if your state is of the ionic character, by the way, what does it mean ionic? It doesn't have much to do with ions. It's still a neutral system, but ionic state is the state which is given as a combination of configurations which expressed in terms of atomic orbitals are ionic, meaning you have a configuration of two atomic orbitals, which are, both of them are localized on the same nucleus A. And this is a configuration given in atomic orbitals where both atomic orbitals are localized on the other atom B. Okay, so we have a combination of configurations localized on A, on one atom, and on the other atom. So both electrons are either on A atom or on B. That's why we call it ionic. So actually, if the state is of the ionic character X, this ratio is greater than 1. So we could say that if we observe, you plot X, you measure X somehow, and you see it's greater than 1, this is an indication that your state is ionic, as opposed to the situation when X is smaller than 1, and which indicates that the state is covalent. Okay, so let's move on. And again, based on this finding, we have defined the ionicity index, which is very handy if you want to quickly find out or detect the character of this state, ionic or covalent. You just need to compute the value of this ionicity index by integrating density, correlation energy density over the domain where X is greater than 1 and divided by the correlation density integrated over the whole space. And if the value is greater than 1/2, it means that this is the status of the ionic character. If it's smaller than 1/2, the status of the covalent character. And of course, we checked that it really reflects the character of the state, molecular state. Okay, but let's come back now to this idea of combining DFT with wave function. I told you that you cannot directly, that it's a bad idea to add correlation energy functional directly to the wave function energy, because you will encounter this correlation double counting problem. So we have to do something smarter. And actually what we proposed was to scale a correlation, in this case LEAP, correlation energy density functional from LEAP by a function P. So P is a scaling function, but it works in the proper way, namely it either scales down the correlation energy or scales it up, depending on the value of X. So the property of the scaling function is as follows. If X is smaller than 1, okay, the function P is also smaller than 1, and if X is greater than 1, which means enhancement, right, or increase of the dynamic correlation, then we scale up the leap correlation function. Okay, that was the idea. The whole difficulty was to find a particular form of the scaling function P to assure good accuracy for grounded excited states of molecules. But the functional that we have proposed is given us here. So this is the energy from the wave function. This is CAS SCF. Okay, but it's just a particular model of the wave function that we assume. It's a multi-reference, multi-configurational wave function. And we added the functional from leap, which is scaled as given here. And actually it works nicely, accurately for different, for grounded excited states. I will show you just a few examples for excited states. So this is a dissociation of hydrogen molecule in either sigma U or sigma G excited states as a function of the bond distance. On the y-axis, we see the excitation energy. On the x-axis, we see the bond distance. And first of all, what we see is that exact, or our model, or approximation CAS pi DFT fits or overlaps very nicely with the exact curve, because for this small system, we can run exact calculations. So we can compare our approximation with the exact values for the energies. And the same for sigma G. So we prove here that the whole idea works for a model system and it's accurate. But there's more than that. Actually, you see that if you look at the ionicity index for the sigma G state at equilibrium distance and when the bond is stretched, we see nicely that the ionicity index changes the values quite abruptly from 0.3, meaning that a system is covalent, or the state is covalent at this bond distance, to 0.8, where the state is identified as ionic. So we see this crossing of the covalent to ionic character of the state when you stretch the bond by using the index. Okay, and this is last but one slide. I will not. So here I'm showing the vertical excitation energies, pi star excitation energies obtained for a number of, it's a subset of molecules that we have investigated, organic molecules, and we compare the excitation energies from different models. I don't want you to actually go through the whole table, because the goal here was to show the accuracy of our method. Before we take a look at it, let's look at mean errors of this direct approach. So the CAS plus leap is this direct addition of leap correlation energy to the CAS, to the wave function energy. And as I already mentioned, this we see what we, I haven't mentioned it, but we see here what we could have anticipated, namely the error, the maximum. The mean average error is very large. It's more than 1 EV for this selection of molecules. It's a large error, but this was expected, because here we see that I'm not saying that it's only the double correlation which is responsible for the error, but actually, but it's basically non-compatible. The feature that the density functional just is not compatible with the wave function, and it leads to obtaining large errors. Moving forward to the mean error from the CAS pi DFT method that we have proposed, we see the error drops. The mean error drops to below 0.1 EV, and the mean absolute error to 0.33, which is reasonably low. And also considering the very high efficiency, low cost, computational cost of the method, this is quite a satisfactory result. So actually this shows that this combination of wave function theory and modified correlation density functional works well for excited states, for ground states also, but I'm not showing it. Okay, so this brings us to conclusions, not to keep you too long. So what we have learned, or what I was trying to tell you about, so reduced functions are simpler and less computational costly to handle than an electron-reduced density, an electron function. So in the ideal world, we would like to get rid of the wave function completely and work only with some reduced function. But as I mentioned, this is not possible for different reasons. The main reason is the lack of exact functionals or highly accurate functionals working for all kinds of systems. So in principle, we could develop quantum chemistry without wave functions free, but ultimately we have to involve some wave function anyway, sooner or later. The most prominent example of really wave function free theory is DFT. But as I mentioned, there are problems with DFT, even despite the fact that we have hundreds of functionals, or more than hundreds of functionals. They have all generic problems that cannot be solved with existing approximations. So modern computational strategies often combine. We have to agree that we have to use wave function theory. So we try to be smart and to combine wave function with DFT to get the best of both worlds via properly defined reduced functions. But for that purpose, we have to modify collection functionals to avoid the collection double problem. And let me acknowledge, this is the last slide, people who have been involved in the work. Oleg Gritsenko, who has been employed in my group for a few years and was a leading force behind this project. Michał Hapka, who is now at the University of Warsaw. Agnieszka Krzemińska and Ewa Pastorczak, members of my group in Łódź. Thank you for your attention.
Thank you very much for this very clear and excellent lecture, which is now open for comments and questions. Oh, Jean-Michel, please.
Okay, the microphone is on. I have thank you for the talk. I think I understood most of it. You're only talking about pure states, right? Because this is the one nice thing about reduced density matrices is that you deal on the same level with pure states and non-pure states. So it's a nice thing too. Of course, computationally wise, you don't really care at this time because everything has zero temperature. But in real life, I think there is an additional advantage of using reduced functions. Anyway, I didn't catch the gain in computational time you get from using this clever method compared with when you need to have the exact result.
Yeah, so first a comment to your comment. So indeed, we may have pure or ensemble state density matrices, but as you know, the representability conditions for this one electron density matrix are for ensemble, and these are ensemble state and representability. So if you are given a density matrix, one electron density matrix, we cannot really tell if it's pure state or ensemble state, right? So if you only work with one RDMs, yeah, most of the time we say, well, we hope it's pure state, but probably it's an ensemble state most of the time. And I must also admit.
Sorry, when you come to mix with wave function, the thing is that on one hand you have
this is
should be a mixed state, and the other one you have a single wave function. So
true, right? Because we construct, we calculate density matrix or density from the wave function. So of course it's pure state and representable. Okay, but to answer your question, so the gain is that if you want to include account for dynamic collation energy in wave function, you have to do expensive calculation because you have to either do CI. Okay, there are different approaches, but the most straightforward is to do CI calculation, which means adding millions or billions of determinants into the wave function to catch the dynamic collation. Of course, there are some perturbation methods which are capable of recovering this missing part, the dynamic collation. but they're also more expensive than in DFT, than correlation density functional. So that was what I meant. Correlation density gives you correlation, the density functional gives you correlation energy for free, right? It's a fraction of the effort comparing to the wave function calculation. So like the total cost, if you take the total cost of the compilation, 99.9 is for the wave function. And this density functional, the time spent on density functional is less than 1%.
Okay.
Okay, we have a question from Michał Chodkiewicz. Are reduced density matrix methods available in quantum chemistry packages? Can we expect that they will become more popular?
Okay, so they are not available in the most widely used quantum chemistry packages, but they are available in at least 2 codes. One is Mario Piri's code. I don't remember the name, but it's open source. It can be used, but I think you would have to contact Mario Piris. And the question, if we can, expect, that they will become more popular, it's hard to say. The honest answer is probably not, because now we have accurate and efficient methods, for example, those combining wave function and density functionals. And then it means that density matrix functional methods are less attractive, because the biggest advantage over DFT of density matrix functionals were that these functionals could treat strong correlation, static correlation. But with the advent of efficient wave function methods for treating these problems makes, as I said, density matrix maybe not that attractive from the point of view of the user. And the second thing is the same as DFT. It's hard to predict if there will be new, more accurate density matrix functions developed, because, of course, there's no straightforward and systematic way of developing functionals. So it's the same problem as with DFT functionals. Maybe someone has an ingenious idea and we have then a functional one day, which is as good as wave functions, but it's hard to predict.
Okay, thank you.
I have a question. So actually I have 2 questions or comments, I don't know. So all these improved methodologies you showed us, they are, the idea is that you now can include dynamic correlation to get better estimates of energy.
Mm-hmm.
But as an experimentalist, X-ray, mostly X-ray diffraction, I would like to have a way to model electron density, which during the modeling, I'm also including the effect of correlation, of dynamical correlation. Would that also be possible, that you can obtain electron density which takes into account dynamical correlation? Or maybe it's not important because it would not be seen in electron density?
That's a good question, actually, because in principle, one could also improve density. So first of all, if you have a wave function which misses dynamic correlation, it means it's only a little bit correlated, right? But by adding this piece from density functional to the energy, we improve the energy, as you rightly said. So we are adding dynamic correlation energy, but we are not improving a density. It's still a density which is connected with the wave function or computed from the wave function. So in principle, one could improve also the density to make it more correlated by running self-consistent calculations. So you would optimize the whole functional, this combined functional with respect to. But then it's doable and it would really bring in dynamic correlation to a density, but then it makes the whole approach expensive and there are problems with convergence. So practically it's at the moment not the way to go. So the answer to your question is that in principle, yes, but in practice, rather not. So it's always done in a post wave function way, those corrections which are added to the wave function. So you don't improve the density.
And my second comment or question is, so we can measure experimentally electron density. As we learned from Jean-Michel, it is also possible to get one electron reduced density matrix from experimental data. So what is actually missing is to also get experimentally 2 electrons density matrices, right? And then we would have everything.
Yes, that would be nice, because then we could get full energy, not only kinetic energy. But it's a question to Jean-Michel if it's thinkable.
Well, I'm not aware of very efficient experimental techniques to recover this 2 particle density matrices. There's maybe only one, and it's all convoluted. So it's I don't think it's tomorrow that we'll get a 2 particle density matrix from experiments. Well, we can always pretend that we have one by taking the 1 particle density matrix and using, you know, the trick, the single determinant trick.
Okay. I do not see more comments and more questions. So let us thank again both speakers for really excellent lectures.